You probably think quantum mechanics is just nerd stuff about teeny tiny particles bouncing around. Wrong. Quantum mechanics doesn't just rewrite the rule book, it sets it on fire. And here's the kicker. According to this theory, you might literally never die. Welcome to one of the most mind-warping ideas in physics, quantum immortality. Sound insane? Good. You're starting to get it. Our instincts whisper that the universe is neat and predictable. Throw a ball, it arcs. Easy. But quantum physics laughs in the face of your intuition because under the hood of reality, everything, and I mean everything, is just a storm of probabilities. Particles aren't following a straight line, they're moonwalking down every possible path at once. Here's what physicist Michio Kaku had to say about it. No matter how absurd quantum theory may seem, it was experimentally correct. Not once, not twice, verified to 11 decimal places. That makes it the most accurate theory humanity has ever conceived. Let that sink in. Take the humble electron. You'd think it's either spinning up or down, but no, it's spinning both up and down until we stick our noses in. That's called superposition. You don't see the magic until you measure it. And then it pretends to have picked a side all along. It's like the universe gaslighting you with mathematics. Still not feeling the vertigo? Let's crack open the legendary double-slit experiment. Picture this. You cut 2 slits in a piece of paper and fire electrons through them. What do you expect? 2 bright lines on the screen behind it, right? Nah, what you get is interference patterns. Waves overlapping, canceling each other like ripples in a pond. And here's the twist. Even when you shoot those electrons one at a time, the pattern still forms. Each tiny electron acts like it walked through both slits at once and interfered with itself. Now here's where it gets spooky. Put a detector at one slit just to check which path the electron takes. And boom, the whole wave show vanishes. No interference. Just boring stripes, like the electrons suddenly decided to behave. That means the very act of observing changes reality. Not metaphorically, literally. This isn't some quirky electron thing. Scientists did this with atoms, then bigger atoms, then molecules made of 2,000 atoms that's basically a protein. They still showed interference, still behaved like waves. In 2019, researchers in Vienna proved it. At this point, it's not quantum mechanics that's weird. It's everything else. So what's the catch? Why don't we see ourselves smeared across rooms in a quantum blur? Because big objects, like you, me, cats, refrigerators, are constantly bumping into stuff. Air, light, stray particles, and every one of those bumps acts like a measurement. Every interaction forces the quantum fog to collapse into the crisp, solid world we're used to. But isolate yourself perfectly, cut off all external influence, and even you would be in a superposition. Not just in 2 places at once, but in multiple realities, unfolding simultaneously. This isn't some fringe theory. This is quantum mechanics doing what it always does, wrecking your brain with the truth. So if you're feeling like you've just walked into a glitch in the Matrix, you're not alone. Richard Feynman, a man who helped invent quantum electrodynamics, said it best. I think it's safe to say that nobody understands quantum mechanics. For centuries, scientists have been fighting tooth and nail over what quantum mechanics actually means. They can't agree on the big picture, but they're all forced to bow to one mind-bending fact. Before we look, particles don't act like little marbles. They act like waves. Everything is a shimmering, probabilistic smear across space. This bizarre behavior is captured by something called the wave function. Erwin Schrödinger, the cat guy, was the one who nailed it. In 1925, he unleashed an equation that told us how these ghost particles slosh around. He plugged it into hydrogen, the simplest atom, and perfect match with the real world. Even better, every single element in the periodic table explained with this one equation. Schrödinger's formula doesn't just describe atoms. It explains why atoms stick together, how molecules form, and why everything you've ever seen or touched exists. That's not poetry, that's physics. Solve his equation, and you can solve the universe. But here's the real punch to the face. How the hell does that probability wave, the cloud of maybes, suddenly collapse into a single, real, concrete thing when we measure it? Enter the Copenhagen Interpretation. It says, until you measure a particle, it lives in superposition, in all possible states at once. Not maybe here or maybe there. It's literally everywhere, simultaneously. And then you look, and bam, it chooses a spot. The odds of finding it somewhere just square the wave function. Thanks Born's rule. But this model, for all its success, doesn't tell us why this happens. So Schrödinger snapped and gave us the most infamous thought experiment in science. The damn cat. Stick a cat in a sealed box with a radioactive atom and a poison trigger. If the atom decays, the cat dies. If not, it lives. But decay is quantum, so it's governed by a probability wave. Which means, according to quantum rules, the cat is both alive and dead at the same time. Two overlapping realities crammed into a box. Until you open it. Then the wave function collapses and reality picks a lane. Live cat or dead cat. So now the question is this. Does the universe wait for your eyes to decide what's real? Einstein hated that. He mocked it. Does the moon exist only if a mouse looks at it? He asked. But in 1957, along came a guy who turned the entire debate on its head, Hugh Everett. Everett said, screw wave function collapse, it never happens. Instead, every single outcome actually happens, just in parallel realities. Welcome to the many worlds interpretation. And it's not just sci-fi fantasy anymore. Big names like Carroll, Deutsch, and Max Tegmark are all in. In this view, when a quantum event occurs, anything uncertain, reality doesn't pick a side. It splits. The universe forks. One version where the particle spins up, another where it spins down. And those two realities, they're not somewhere else. They're right here, stacked on top of each other. They just can't talk to each other, except sometimes, in weird quantum interference cases. And here's where things get chilling. Imagine you're in a car crash. You've got a 50-50 shot at surviving. In many worlds, there's now two versions of you, one dead, one alive. But your consciousness, it can't experience death. Dead brains don't perceive. So you always find yourself in the world where you survive. No matter how impossible the odds, no matter how hopeless the situation, there's always one version of reality where you walk away, and that's the only one you'll ever know. Your consciousness is a survivor, not by chance, but by quantum law. So maybe death, at least from the first-person perspective, never actually arrives. You just keep shifting into the universes where you're still breathing, still standing, still you. Perhaps reality is indeed so bizarre, physicist Anthony Aguirre admits, that we subjectively survive any death that's instantaneous and binary. And Hans Morevi puts it bluntly. We always find ourselves in those worlds where we are, never in those where we are not. Max Tegmark isn't your average physicist. He didn't just ask whether parallel universes might exist. He asked how you could prove it. Not with some abstract equation, not with chalkboard wizardry, but with an experiment so reckless it comes with a disclaimer, do not try this at home or anywhere ever. Here's the setup. Picture a machine. It's basically quantum Russian roulette, except instead of a revolver, you've got a quantum-triggered machine gun. Every second, it flips a 50-50 quantum coin. Heads, you hear a click. Tails, you don't hear anything ever again. Now imagine putting your head in the line of fire. Yes, your actual head. According to classical physics, you've got a snowball's chance in hell. After a few clicks, it's lights out. The odds of surviving for just 60 seconds? Less than 1 in a quintillion. You're not just dead, you're statistically irrelevant. But here's the Everett twist. If parallel universes are real, the gun fires in both outcomes. In one universe, you're gone. In the other, you live to hear another click. And crucially, you're only conscious in the branch where you survive. The dead don't get to reflect on how unlucky they were. So from your perspective, you'll keep hearing click after click after click, and after 10 straight clicks, you've basically proven that quantum immortality is real. Not to the world, not to scientists, just to yourself. In all other universes, people are scraping your remains off the floor and nominating you for a Darwin Award. Tegmark didn't invent this idea to go viral. He dug it out of the logic of Everett's many worlds interpretation. And while Hugh Everett himself never officially wrote about quantum immortality, his biographers said he believed in it deeply. Not the Hollywood version, not the "you'll live forever in paradise" version, the grim, cold version. The one where you survive because there's always some version of reality where you don't die, no matter how brutal or broken that reality is. You won't always be young or healthy or happy. You'll just keep going, through sickness, through horror, through decay. Even when life becomes a crawl through hell, somewhere you're still moving forward. Welcome to the nightmare logic of immortality by quantum indifference. Philosopher David Lewis put it chillingly clear. The observer must expect to survive forever, not happily, but indefinitely, like the myth of Tithonus, eternal life without eternal youth. Sounds insane, doesn't it? But this idea, this internal monster of logic, is one of the most serious and popular interpretations of quantum theory. No, not every physicist buys it, but the argument is clean, brutal, and airtight. Once you open the door to Everett's multiverse, you don't get to pick which version of it you like. This is the conclusion staring back at you. So in this video, we're going to dissect it all. The believers, the skeptics, the math, the madness, and you'll walk away with the one thing physics never promised, a personal stake in the outcome. Tegmark opens our mathematical universe with a memory. He was just a kid, riding his bike on an empty road. The sun was up, everything was normal. He was approaching an intersection. A second later, I died. I let go of the pedals and hit the brakes, but it was too late. Headlights, radiator grille, 40 tons of steel screaming like a modern dragon. I managed to see the driver's eyes. Time slowed down for me. My life flashed before my eyes, and my last thought was, I hope this is just a nightmare. Alas, in the morning, I felt that this was reality. Here's the thing. Reality lies. It lies in plain sight. It tells you that trucks are solid, that you're solid. But what physicists have known for decades is that the world around us, the real world, is practically empty. It's made of atoms. And atoms, they're almost entirely nothing. Just clouds, whispers, phantom forces. 99.95% of an atom's mass is locked in its nucleus. But that nucleus is a dot in a cathedral of emptiness. You're not really touching anything. You're being repelled. Your skin never touches the chair you sit in. Everything is held together by electrical force fields, not solid matter. And if that sounds like sci-fi, brace yourself, because it gets weirder. Subatomic particles, they don't play by our rules. They can be in multiple places at once. They flicker, they blur, they refuse to choose until someone looks. So here's the million-dollar question. If your body is made of particles, why can't you be in two places at once? Enter the Copenhagen Interpretation, the original way to make sense of the madness. 3 seconds before the accident, I subconsciously decided whether to look only to the left, where I always turned and where there were never any cars, or to glance to the right, just in case. That morning, a spontaneous, unfortunate decision brought me to the brink of death. Everything depended on whether a single calcium atom would hit a specific synapse in the prefrontal cortex of my brain, causing a specific neuron to fire and send an electrical signal that would trigger a whole cascade of activity in other neurons, jointly encoding the thought, "Don't worry." So, if the calcium atom had initially been in two slightly different positions, half a second later my eyes would have been looking in two different directions. A couple of seconds later, my bike would have been in two places at once, and a little later, I would have been both alive and dead at the same time. If I am in two different places in two parallel universes, then one of my copies will survive. If we apply the same reasoning to all the other ways I could die in the future, it seems that there will always be at least one parallel universe in which I will never die. Since my consciousness only exists where I am alive, does that mean that I am subjectively immortal? If so, will you also feel immortal? If you open any classic textbook on quantum mechanics, you will see the following statement. Atoms can be in several places at once, but large objects cannot. That's nonsense, right? After all, we ourselves are made up of atoms. If they can be in different places, then why can't we? In search of an answer to this question, Tegmark, while still a student, went straight to a professor from the Nobel Committee and asked the question point blank. 20 minutes later, he walked out, stunned. It was only a couple of years later that he realized it wasn't his lack of understanding. Even the giants of physics don't agree. They argue, they squabble. And behind all the math, one thing becomes clear. Reality is not just weird. Our universe is like a giant construction set. Everything in it, from water and stars to your smartphone, is made up of the same parts, 80 stable atoms. The only difference is how many of each part are needed and how they are arranged. For example, your body is almost 2/3 hydrogen, which, together with oxygen, forms water, filling every cell of your body. Carbon forms the basis for all organic molecules, while nitrogen and calcium form proteins and bones, allowing you to think and move. The idea of atoms is not new. Plato once believed the universe was made of perfect shapes. Fire consisted of sharp tetrahedrons, which is why it caused pain with its corners. Water flowed thanks to the rounded shape of icosahedrons, and the earth was solid because of the dense arrangement of cubes. It took 2 millennia for modern atomic theory to develop. Today, we can not only obtain images of individual atoms under a microscope, but also manipulate them. We know that atoms themselves are not indivisible. They are also similar to miniature construction sets. Atoms consist of only 3 types of smaller particles: protons, neutrons, and electrons. They form a miniature planetary system. Electrons revolve around a compact atomic nucleus, a cluster of protons and neutrons. Just as gravity keeps the Earth near the Sun, electrons are attracted to protons by electrical interaction. Electrons have a negative charge, protons have a positive charge, and opposite charges attract each other. Electrons help atoms bond with each other to form molecules. When atomic nuclei and electrons rearrange themselves without changing their number and type, we call this a chemical reaction. This can happen quickly, like a forest fire, or slowly, like the growth of a tree. For centuries, alchemists tried to transform some atoms into others. Most often, they tried to turn lead into gold and failed, but not because it was impossible, but because they lacked energy. Protons in nuclei are held together by an incredibly powerful force, the strong nuclear interaction. To overcome it, monstrous temperatures of millions of degrees are needed. Such temperatures exist in stars. When the universe was young and hot, it contained only hydrogen atoms. But as it cooled, protons and neutrons began to stick together, forming heavier atoms. The center of the sun is still hot enough for hydrogen to turn into helium. Ordinary atoms such as carbon, nitrogen, and oxygen are relatively easy to obtain. Stars eject them when they die. But gold is only created during supernova explosions. These are extremely rare events when a dying star briefly becomes brighter than the entire visible universe. Not surprisingly, chemists have been unable to do this. So atoms consist of protons, neutrons, and electrons. But what if these particles are also made of something? History has taught us to answer such questions simply. You need to collide these particles at tremendous speeds and see if they disintegrate. Physicists have done this at all the major colliders in the world. Electrons seem to be truly indivisible. Even at CERN, after accelerating them to nearly the speed of light, we were unable to split them. Protons and neutrons, however, turned out to be complex particles. They consist of even smaller parts called quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. During powerful collisions, scientists discovered a whole zoo of new particles with exotic names: pions, kaons, and so on. Most of them also consist of quarks, but of other types: strange, charmed, charming, and true. There are also special particles, carriers of natural forces. Photons carry light and electromagnetism, while W and Z bosons are responsible for radioactivity. Gluons act as cosmic glue, holding quarks together, and the recently discovered Higgs boson gives other particles mass. There is also the elusive neutrino. They hardly interact with ordinary matter. A neutrino can fly through the entire Earth without even noticing it. All these particles have their evil twin, an antiparticle. When they meet, they annihilate each other, destroying each other and turning into pure energy. Well, this is where our knowledge reaches the limits of modern accelerators. It is interesting how particles transform into each other. In the Large Hadron Collider, when two protons collide, a Z boson can be created, which weighs 97 times more. This seems impossible, as if two Ferraris collided and a cruise ship was created. But Einstein explained it. Energy can be converted into mass according to the formula E equals mc squared. In a sufficiently powerful collision, part of the kinetic energy becomes new particles. The same happens with momentum and other physical quantities, which are always conserved. Fundamental particles can be thought of not as particles, but as sets of these conserved quantities. And here an interesting question arises. What are these quantum numbers themselves made of? The answer is simple: nothing. They are just numbers. Cats also have energy and charge, but they also have many other properties. A name, a smell, a personality. Elementary particles, on the other hand, are completely described by a set of numbers and seem to have no other properties. Ultimately, all particles are described by three simple numbers: energy, charge, and spin. They have no properties other than mathematical ones. This brings us back to Plato's idea. The most fundamental building blocks of the universe are purely mathematical objects. For more on this, see the video about symmetry. Nature is like a multi-level construction set. When playing with ordinary Lego, a child simply rearranges ready-made blocks. If he were rearranging atoms, it would be chemistry. Rearranging neutrons and protons is nuclear physics, and the collision of particles at near-light speeds is particle physics. And it seems that the details of the deepest level are purely mathematical objects. But it is not only matter that consists of building blocks. Light does too. In 1905, Einstein showed that light consists of particles called photons. 40 years earlier, Maxwell discovered that light is oscillating electromagnetic waves. The frequency of these oscillations determines the light, and their strength determines the brightness. We give electromagnetic waves different names depending on their frequency: radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, and gamma rays. These are all forms of light, and they all consist of photons. Einstein understood that the energy of a photon is equal to its frequency multiplied by Planck's constant. This constant is very small, therefore a normal photon contains little energy. But when you spend a few seconds on the beach, you are warmed by a sextillion photons, which is why light seems continuous. Einstein received the Nobel Prize for this idea. He explained why the ability of light to knock electrons out of metal depends on frequency rather than intensity. Low-frequency photons simply do not have enough energy to do this. Solar batteries and digital camera matrices work on this principle. Planck also received the Nobel Prize for solving another mystery. Physicists could not explain why heated bodies do not emit an infinite amount of energy at high frequencies. The answer turned out to be simple. Light can only be emitted by individual photons, and a lot of energy is needed to create high-frequency photons. That is why we do not go blind from the gamma radiation of every warm object. If everything consists of particles, what laws do they obey? If we know what all the particles in the universe are doing at a given moment, can we predict their behavior in the future? If such equations exist, we could predict everything, from the trajectory of a ball to the winners of future Olympic Games. And I have good news for you. Such an equation exists. It is Schrödinger's equation, but it does not predict exactly how particles will behave. Even almost 100 years after its discovery, physicists are still arguing about its meaning. Everyone agrees on one thing: microscopic particles do not obey the classical laws that we learn in school. Since an atom resembles a planetary system, it is natural to assume that electrons revolve around the nucleus, according to Newton's laws, like planets around the sun. If we calculate this for a hydrogen atom, we find that the electron revolves at approximately the same speed as measured in the laboratory. A real triumph. But there is a problem. According to classical physics, a rotating electron should emit energy and fall onto the nucleus in a billionth of a second. The reality is obviously different. Hydrogen atoms have existed for billions of years. The difference between theory and practice was 28 orders of magnitude. It was the worst prediction in the history of physics, until this anti-record was broken by the calculation of dark energy, which was off by 123 orders of magnitude. It became clear that completely different laws operate in the micro world. Classical physics, which perfectly describes the movements of planets, proved powerless in the world of atoms. Nature has prepared new rules of the game for us. Quantum mechanics, described by Schrödinger's equation. In 1913, Niels Bohr proposed a revolutionary idea. What if the movement of an electron in an atom does not occur smoothly, but in jumps, like in old Charlie Chaplin films? He suggested that an electron can only move along specific orbits. This simple idea solved the mystery of the unstable atom. The electron could no longer fall onto the nucleus because when it is in the innermost orbit, there is no lower orbit for it to fall into. When the electron jumped from a high orbit to a low one, it emitted a photon of light, and to rise higher, it needed to absorb a photon with the appropriate energy. Bohr's model brilliantly explained the mysterious dark lines in the spectrum of sunlight. Each type of atom could emit and absorb light of only certain colors, like a unique light fingerprint. For the hydrogen atom, the calculations matched the experiment perfectly. Bohr received the Nobel Prize for this, but his model only worked for the hydrogen atom and could not explain the behavior of more complex atoms. Louis de Broglie went further and offered a bold explanation. Electrons are waves. Just as sound waves in a musical flute can only sound certain notes, so electron waves can only exist in an atom in certain orbit. This also explained why an atom cannot collapse. If you try to compress a wave into a very small space, it will immediately begin to spread out. Werner Heisenberg developed this idea into his famous uncertainty principle. It is impossible to know both the position of a particle and its velocity at the same time. The harder we try to squeeze an electron into a small space, the faster it begins to move, trying to escape. After hearing de Broglie's dissertation, Erwin Schrödinger set out to derive wave equations for these particle waves. This is how he opened the door to modern physics. On a new mathematical foundation, quantum theory experienced explosive growth. In just a few years, many mysteries were explained. Quantum physics gave us lasers, transistors, computers, and smartphones. Schrödinger's equations are a stunning example of scientific data compression. Imagine that more than 20,000 spectral lines, carefully measured in laboratories around the world, can be described with just 3 numbers. It's like reducing an entire book to a single sentence. In classical physics, everything is simple. To describe the motion of a planet, it is enough to know its position and velocity. But in the quantum world, a particle can be in many places at once. Instead of a precise position, we have a probability cloud, a wave function that shows where the particle can be found. Take, for example, an electron in a hydrogen atom. It does not revolve in orbit like a planet, but exists everywhere around the nucleus at the same time. It is simply more likely to be found in some places than in others. These are unusual waves like in a lake. In waves, the water itself oscillates. But here, it is the probability of finding a particle in a particular place that oscillates. Physicists call this quantum superposition, the ability of a particle to be in several places at once. But here a mystery arises. Why do we never see a cat in different places at the same time? After all, a cat consists of atoms, and atoms can be in superposition. Bohr and Heisenberg proposed radical solutions, known as the Copenhagen Interpretation. In their opinion, when we observe a quantum system, its wave function instantly collapses, and the particle ends up in one specific place. Many people did not like this explanation. Einstein, for example. God does not play dice, he said, unwilling to accept that chance is inherent in the very nature of reality. He was also troubled by the fact that the observer plays such an important role. The founders of quantum theory made a bold call. Measurement is more real than the wave function. And you know what? You can't blame them. Measurement is what we actually see. You look, you get a result. Simple, tangible, but that simplicity was a trap. The Copenhagen Interpretation, the reigning dogma, only made things murkier. What even counts as an observation? Do you need a human eye, a conscious mind, or is a security camera good enough? And what's the math behind this so-called collapse of the wave function? No one could say. Roger Penrose wasn't exaggerating when he said there are more opinions on quantum mechanics than there are physicists. And some manage to hold several contradictory views at the same time. As Schrödinger himself noted, if atoms can be in superposition, why can't larger objects composed of them do the same? To explore this mystery, he came up with a famous thought experiment. Imagine a cat in a closed box with a radioactive atom and a Geiger counter that releases poisonous gas when triggered. The point of the experiment is to link the state of a microscopic atom to something larger and tangible. If the atom decays, the detector picks up the radiation, releases the gas, and the cat dies. If it does not decay, the cat lives. According to quantum mechanics, most of the time the atom is in a superposition of decayed and undecayed states simultaneously. Due to entanglement, the superposition extends to the detector and the cat. After a while, the wave function of the entire contents of the box is in superposition. In one state, the atom is not decayed, the gas is in the tube, and the cat is alive. In another state, decay has occurred, the gas has filled the box, and the cat is dead. It turns out that the animal is both alive and dead at the same time. When we open the box, we take a measurement, the wave function collapses, and the cat is either alive or dead. Today, this experiment is remembered to show the strangeness of quantum mechanics. That was not Schrödinger's intention. He wanted to demonstrate that such an understanding of quantum mechanics is absurd. Let's rip open the Schrödinger experiment and look at the guts. Superposition, entanglement, and measurement. Are they confusing? Sure, but do they hold up? Let's find out. First up, superposition. The idea that a quantum object can be in multiple states at once. That's not sci-fi, that's cold hard experimental fact. You've probably heard of Thomas Young's double-slit experiment. Fire a single electron at a barrier with two slits, and somehow it goes through both. Not either or, both. It is easier to understand with waves. A wave is not a point, and it is clear how the peaks and troughs of different waves create interference. So, everything is fine with superposition. Now let's crank it up. Entanglement. Picture two electrons launched straight at each other. We know that they will bounce off each other, but we do not know in which direction. Their momenta are in superposition, but the second you measure one, the other's outcome is locked in instantly, no matter the distance. Even if one's next to your coffee and the other's halfway to Alpha Centauri, measure one and boom, you know the other. This isn't magic, it's quantum entanglement. Einstein called it spooky action at a distance, but it's real. The essence of entanglement is that after interaction, the electrons no longer have their own wave functions. Their state is described by a single common function, so measuring one instantly affects the other. If we continue this line of thought, it turns out that there is only one wave function describing the state of the entire universe. When we talk about individual wave functions, we must remember that entanglement occurs at the moment of interaction. So, everything is clear with superposition and entanglement. They are fundamental components of quantum theory. But then comes the last piece of the puzzle, the one that still makes physicists twitch: measurement. Why does a quantum system obey one set of rules when no one's looking, and another when you peek? That's not just bizarre, it's offensive to logic. Dig deeper and you'll realize something. A measurement is just another interaction. Electrons bounce off photons, photons hit detectors. We know how this happens. Their wave functions evolve according to Schrödinger's equation. So why do we need special rules for measurements? If we remove them from Schrödinger's experiment, it turns out that the superposition of a decayed and undecayed radioactive atom becomes entangled with the detector and, as a result, with the cat itself. And when you open the box, guess what? You get entangled too. No collapse, no divine intervention, just pure, relentless quantum law. So how do you end up seeing just one outcome, a dead cat or a live cat? Because there are now two versions of you, one standing over a corpse, one relieved to see a living feline. These versions will never meet. They're split forever. And what split them? Decoherence. The final twist in this quantum tale: air molecules, photons, background radiation, the endless noise of reality. When particles in superposition interact with their environment, they entangle with it too, fast, brutally fast, and that causes the wave function to branch. So in Schrödinger's experiment, when the atom decays or not, the detector reacts one way or another. The air reacts differently in each case. Light scatters differently. The wave function splits, and two yous are born, one watching a dead cat, the other staring at a live one. This isn't speculation. It's the core of the many worlds interpretation, formulated by Hugh Everett. If he is right, then such bifurcations of reality occur with a frequency that can tend to infinity. Right now, in your body alone, 5,000 radioactive decays happen every single second. Each one spins the universe into another thread of reality. You don't feel it, but it's happening. Yes, we're radioactive. Each decay either occurs or does not occur, creating a superposition. When the decay occurs, the atomic nucleus interacts with its surroundings and becomes entangled. The universe branches out. The constant emergence of parallel worlds sounds strange, but it follows naturally from mathematics. The many worlds interpretation seems clearer than the Copenhagen interpretation. There are only wave functions and the Schrödinger's equation to which they obey. Quantum mechanics becomes more logical without the collapse postulate. There is only continuous evolution, according to Schrödinger's equation. There are no different rules for observation and non-observation. Perhaps the early researchers of quantum theory got it all wrong, and wave functions create a more complete picture of reality than measurement results, which show only a fragment of it. In this picture of the world, the universe becomes deterministic again, and everything happens with 100% probability. We just don't notice it, because we only see a tiny part of the multiverse. But mathematics says there is much more. Let's return to Max Tegmark's memory of riding his bike. A single atom in his brain, existing in two states at once, could have caused him to make two different decisions simultaneously, to look right and not to look. In one reality, he survived. In another, he did not. Whether a particular neuron fires at a particular time depends on whether the sum of its input signals exceeds a certain threshold. And this can make a neural network extremely unstable, like the weather or a pencil standing upright. I was riding my bike and deciding whether to look to the right. Imagine that my spontaneous decision, which allowed me to survive, depended on whether a single calcium atom would hit a specific synaptic connection in my prefrontal cortex, causing a specific neuron to emit an electrical signal that triggers a whole cascade of actions by other neurons in the brain under the general conditional name, let's look. If that calcium atom had ended up in two places at once, half a second later my eyes would have been looking in two directions at once, and my body would have been in two places at once, one of which would have been the morgue. It would have been my own version of Schrödinger's cat experiment, where I would have played the role of the cat. I was tormented by a simple question. If particles can be in several places at once, why can't we see it? I found the answer in an old dissertation by Hugh Everett, bought in a bookstore that sold anarchist literature. His idea turned out to be strikingly simple. The wave function never collapses. Never. Picture this. You stand a playing card on its edge. Close your eyes and let it fall. According to quantum mechanics, it doesn't fall one way or the other. It falls both, face up and face down. When you open your eyes, something wild happens. Your consciousness also splits. In one universe, you see it face up and smile. In another, it's face down and you groan. These two versions of you exist simultaneously but are unaware of each other. Each version of you thinks it's the original. Each one believes this is the one true reality. This division occurs constantly with every quantum event. When a cosmic ray causes or does not cause a mutation. When weather conditions lead or do not lead to a hurricane. When you make one decision or another. History constantly branches out, creating countless parallel universes. There are more of them than grains of sand in our entire universe. Each one plays out its own version of events, every possible story that does not violate the laws of physics. This discovery shook me. In May 1999, while awaiting the birth of my first child, I was tormented by strange thoughts. I knew that in some universes the birth would be successful. In others, it would not. What was I hoping for then? After all, I would find myself in all these realities at the same time. Hoping for a good outcome in most universes is also pointless. This fate is already predetermined by quantum laws. Perhaps our emotions cannot keep up with quantum mechanics. Everett made this painfully clear. We don't feel like we're spinning around the sun at 30 kilometers per second, but we are. And just like that, we don't feel the universe splitting apart beneath our feet over and over again. But if Everett is right, if the wave function never collapses, but just keeps branching, then where the hell does all the randomness come from? Let's say you're flipping a coin. You toss it, it spins, and, according to quantum mechanics, it doesn't land heads or tails. It lands both. The coin enters a superposition, and reality splits. In one branch, you see heads. In another, tails. And each version of you sees only one outcome. If you flip the coin 4 times, you will get 16 possible outcomes. In most cases, about half of the coins will land heads up. Only in 2 of the 16 outcomes will all 4 flips give the same result. As the number of tosses increases, the picture becomes more interesting. Mathematician Emile Borel proved that if you toss a coin an infinite number of times, in almost all branches of reality you will see that the coin lands heads up exactly 50% of the time. This means that almost all of your copies in parallel worlds will observe a sequence that appears random, even though the Schrödinger equation governing the wave function is completely deterministic. If you record the results as 1s and 0s, the resulting sequence will look like a random set of numbers. Borel's theorem states that not only will the ratio of heads to tails be approximately 50-50, but the sequence will also appear random, with no repeating patterns. Interestingly, this illusion of randomness is not unique to quantum mechanics. Imagine a future where technology can clone you in your sleep, perfect copies dropped into rooms numbered 0 and 1. When your clones wake up, they don't know which room they're in. It feels random. Run the experiment over and over, and you get a string of 0 and 1 that looks just like your coin flips. Why? The fact is that Schrödinger's equation describes you as a single entity, transforming into multiple versions of yourself in different universes. This is similar to cloning in our example. You are one, but after a quantum event, you become several copies, each of which sees only its own result and considers it random. Hugh Everett's work remains controversial, but I am sure he was right and the wave function never collapses. Someday he will be recognized as a genius equal to Newton and Einstein, at least in most parallel universes. In our universe, his theory was ignored for decades. He abandoned physics, became withdrawn, began smoking and drinking heavily, and died of a heart attack in 1982. In our universe, he was not immediately accepted into the physics department at Princeton. Due to lack of time, his dissertation remained his only work. In other universes, he was probably accepted immediately and managed to gain recognition in traditional fields of science. This could have been the beginning of a career similar to Einstein's. The special theory of relativity was also met with suspicion, especially considering the fact that it was put forward not by a representative of the academic community, but by an employee of the patent office. But it could not be ignored, since Einstein had already made a name for himself with other discoveries. Just as Einstein, upon entering the academic world, was able to discover the general theory of relativity, Everett, having received a professorship, made new breakthroughs just as remarkable as the first. How I wish I knew what exactly he discovered. So here it is. The answer we've been chasing all along. Why don't we ever see things in 2 places at once? The answer hits like a plot twist. Because quantum mechanics demands secrecy. An object can be in 2 places at once, but only as long as that fact stays hidden. The moment anything, even a single rogue particle, finds out where the object is, the illusion shatters. Superposition collapses. Imagine what would happen if a single photon of light were reflected from an object located in 2 places at once. In a nanosecond, this photon would find itself in 2 different positions, carrying information about where the object was located. The information about it ceases to be secret. That is why we never see macro objects in 2 places at once, not because they are large, but because they are difficult to isolate. A bowling ball collides with trillions of photons and molecules every second. Its superposition is destroyed faster than we can blink, but a single electron in a vacuum can exist for about a second without colliding with other particles. This is more than enough to see its quantum properties. Inside an atom, an electron makes a complete revolution in a trillionth of a second, so it can easily be found on all sides of the nucleus at once. No human observer or consciousness is needed to destroy quantum superposition. Just one particle learning the secret. The quantum world disappears not because we look at it, but because it is impossible to look at it without destroying its mystery. Nature turned out to be deeper and more interesting than we thought. Parallel realities exist. but they remain forever separated. As soon as information about them becomes available to the outside world, they lose their ability to influence each other. The quantum world does not disappear. It simply keeps its secrets very well. In recent years, there has been a surge of interest in quantum computers. They could use quantum effects to accelerate the solution of certain tasks, such as decrypting the codes that protect your bank card. Modern computers would take longer than the age of the universe to do this. A quantum computer could do it in minutes. As quantum computing pioneer David Deutsch says, quantum computers distribute information across a huge number of versions of themselves in the multiverse. In effect, they use parallel universes as a computing resource. Building such a machine is incredibly difficult. The main enemy? Decoherence, the destroyer of quantum dreams. Quantum information has to be isolated perfectly, or else the surrounding environment rips it apart. A single stray particle, a whisper of heat, a breath of air, and poof, your quantum superposition is dead. Right now, the best quantum computers on Earth can barely hold a few qubits. That's quantum bits. Your phone? It handles billions of classical bits like it's nothing. The quantum world is fragile, temperamental. It needs a deep vacuum and a temperature close to absolute zero. So here's the question that blew up the physics world in 2000. What if your brain is a quantum computer? That's what legendary physicist Roger Penrose dared to suggest. A regular computer works with zeros and ones, binary, clean, but a quantum computer? It runs in both states at once, 0 and 1, superposition. It spreads its calculations across parallel universes and pulls results from all of them. It doesn't compute faster, it computes everywhere. But remember, it only works if the quantum state stays secret. No outside interference, no peeking. What about a warm and humid brain? Max Tegmark decided to test this mathematically. He applied the decoherence formula to neurons. These are nerve cells that transmit electrical signals in the brain by moving charged sodium and potassium atoms. When a neuron is activated, about 1 million sodium atoms move inside the cell. If the brain is indeed a quantum computer, then the neuron must be in a superposition of active and inactive states. 1 million sodium atoms must be both inside and outside the cell at the same time. But a quantum computer only works as long as its state remains a secret to the outside world. How long can a neuron keep its state secret? The calculations yielded an interesting result. Quantum superposition in a neuron collapses in a fraction of a second. This is the time it takes for a random water molecule to collide with one of the sodium atoms, measure its position, and destroy the superposition. It turns out that if your brain worked like a quantum computer, you would have to think at a speed of 10 trillion thoughts per second. It would be beautiful, almost poetic, to discover a quantum computer inside our heads. But the numbers tell a different story. It is impossible to build a quantum computer in a warm, humid place where information constantly leaks into the environment. So, instead of dreaming about quantum brains, Max Tegmark asked a darker question. Can we prove that parallel universes exist? And then, disturbingly, he came up with a way. He called it quantum suicide. Here's how it works. Imagine a quantum machine gun. No joke. It's wired to fire or click, depending on the outcome of a quantum measurement. A particle is placed in a superposition of two states. The machine measures it. If it's in state A, click. If it's in state B, bang. Now say it fires once per second. What do you hear? If reality collapses like Copenhagen says, you'll hear 1 or 2 clicks, then a shot. End of experiment, end of story. But if Everett's many worlds interpretation is right, then things get weirder. With every quantum trigger, the universe splits. In one branch, you die. In another, you live. And only the living you can still hear the clicks. From your perspective, you hear click, click, click. You survive. Every time. Always. After 10 clicks, you can be 99.9% sure the wave function never collapsed. You just slipped through the cracks in reality. To verify that the machine gun works, you glance at it. Sure enough, shots and clicks alternating, just like it should. However, there is a catch. If you call a friend to watch, they will see you dying quickly because they remain alive in all universes. Not just those where you survive. The only thing he will be sure of is that you are crazy. Many physicists would be delighted if, on their deathbed, an omniscient genie answered any physical question. Now imagine you wanted to push it even further. Link the quantum trigger to something bigger, say an atomic bomb. Then you would find yourself in those universes where all your friends are either dead or alive. But after that, they would hardly remain your friends. If you consider all the potentially deadly events in your life to be experiments in quantum suicide, doesn't that mean you should expect immortality? The answer can be obtained in a simple way. Just wait and see. If one day, after a series of incredible coincidences, you find yourself to be the oldest person on Earth, then most likely that is the case. But don't expect the people around you to become incredibly old as well. As in the quantum suicide experiment, only you will remain alive in the branches of reality where you survive. The thought experiment with quantum suicide is very similar to Schrödinger's cat experiment. All you need to do is place the observer inside the box. Only those whose lives depend on quantum uncertainty can distinguish between interpretations of quantum mechanics. According to the Copenhagen Interpretation, after the first test, the probability of survival is 50%. With each subsequent test, it is halved. After a sufficient number of attempts, the probability of survival becomes practically zero. But in Everett's universe, there's no collapse. Every test branches reality again, and the only you left to observe is the one who never dies. That's quantum immortality. But Max Tegmark, who first proposed this thought experiment, made one thing crystal clear. This only works if you do it right. There are 3 brutal requirements. 1. The source of randomness must be quantum, not classical, so that you really end up in a superposition of alive and dead. 2. Death must occur faster than you can realize the outcome. Otherwise, you will simply get a very unhappy version of yourself who knows about your inevitable death. 3. The experiment must be guaranteed to kill you, not just injure you. In 2001, philosopher David Lewis gave his first and only lecture on quantum mechanics. The title, How Many Lives Does Schrödinger's Cat Have? 4 months later, Lewis was dead. The lecture was published posthumously and had left behind a chilling idea. If the many worlds interpretation is true, if reality branches with every quantum event, then the observer must always end up in the branches where they survive. No matter how slim the odds, no matter how close the call, your consciousness can only persist in the timelines where it didn't die. Sounds like immortality, right? But Lewis wasn't celebrating. He painted a darker picture. Yes, you survive, but not in glory, not in health, not even in dignity. According to Lewis, you survive because you have to, trapped in a dwindling sliver of probability, an echo of yourself. The result? An eternity not of life, but of decay, endless rot, eternal aging, a modern typhon, unable to die but unable to live, a mind smeared across universes, desperately clinging to the last flickers of awareness. Max Tegmark disagreed. He argued the logic breaks down in the real world. Why? Because real death doesn't happen like a gunshot or a coin flip. It's not a binary event, it's gradual. You don't just vanish, you fade. Neurons don't all switch off at once. Consciousness dissolves slowly, like fog in the morning sun. There is no sharp line between life and death, only a gray spectrum of deterioration, and that destroys the mechanism of quantum immortality. Yes, there may be branches where you dodge each bullet, survive each heart attack, each cancer, each fall. But with every close call, the measure, the amplitude of those branches gets smaller. You're not skipping death, you're leaking into oblivion. Imagine that you are a wave function. With each quantum choice between life and death, the amplitude of probability of those worlds where you survive becomes smaller and smaller. Your existence becomes less and less significant in the overall structure of the multiverse. It's like a radio signal that gets weaker and weaker until it turns into a barely audible whisper amid cosmic noise. You may formally continue to exist, but at such an insignificant level, can we talk about full consciousness? Many scientists who embrace the multiverse still reject quantum immortality. David Deutsch, one of the founders of quantum computing, slams the idea. In The Beginning of Infinity, he writes, "This way of applying probabilities does not follow directly from quantum theory. It requires an additional assumption, namely that when making decisions, one must ignore histories in which the decision maker is absent. My opinion is that this assumption is false. Physicist Carroll, another proponent of the many worlds interpretation, also rejects the idea of quantum immortality. Carroll emphasizes, when the world branches out, future versions of you become different personalities. You cannot choose one of them as the real one and ignore the demise of the others. I am now not entirely convinced of the reality of the quantum suicide experiment or the reality of quantum immortality, since both depend critically on the existence of an infinitely divisible mathematical continuum in nature, which I strongly doubt. But who knows? When the fateful day comes and you are sure that your life is coming to an end, remember not to tell yourself that nothing will remain of you, because that may not be the case. Perhaps you will personally see that parallel universes exist. The battle over how to interpret quantum mechanics has raged for over a century. Do we believe in wave function collapse, or do we embrace the multiverse? In that time, an entire zoo of interpretations has emerged. Copenhagen, many worlds, transactional, relational, the list goes on. For decades, it seemed the arguments would never end. But now, something's changed. Everett's ideas, once ignored, then ridiculed, are reshaping the way we see the universe. Physicists realized that even if you throw out the wave function collapse and keep only Schrödinger's equation, you'll still feel like the wave function collapses. Why? Because you don't see the parallel universes. You never have, you never will. And for the longest time, people thought quantum weirdness ended at the atomic scale. But we were wrong. The double-slit experiment wasn't just repeated with electrons. It was scaled up to atoms, then giant molecules made of 1,000 atoms. Today, researchers like Keith Schwab are putting metal rods, objects visible to the naked eye, into quantum superposition. Anton Zeilinger's team in Vienna, they're already dreaming of running the experiment with a virus. If we imagine that a virus has a primitive consciousness, then a multiverse interpretation becomes inevitable. Extrapolating this to humans would only be a quantitative difference, not a qualitative one. The same group of scientists showed that the quantum properties of photons are preserved when they travel through 89 kilometers of space. The experimental verdict has been delivered. The world is indeed strange, and we need to learn to live with it. According to recent estimates, more than a quarter of the U.S. gross national product is now based on inventions that have emerged thanks to quantum mechanics. From lasers to computer chips, and the latest technologies such as quantum cryptography and quantum computing explicitly use the multiverse and only work if the wave function does not collapse. These breakthroughs have caused significant changes in the views of physicists. Max Tegmark conducted surveys in 1997 at a quantum conference and in 2010 at Harvard. He asked scientists which interpretation they preferred. It turned out that a radical shift had taken place. After decades of dominance by the Copenhagen Interpretation, its support fell from 30% to 0. In contrast, Everett's many worlds interpretation, which went unnoticed for 10 years and then was harshly criticized for 25 years, topped the rankings in 2010. As Konrad Lorenz famously said, every great idea passes through 3 stages. First, it is ignored, then it is attacked, and finally, it is accepted as obvious. Everett's parallel universes are now between the second and third phases. So, if we live in a multiverse, how should we perceive the world and our lives? How can we find meaning where absolutely everything that is not prohibited by the laws of physics happens? On October 27, 1962, at the height of the Cuban Missile Crisis, a Soviet submarine off the coast of Cuba was surrounded by American destroyers. The Americans dropped depth charges in an attempt to force the submarine to surface. The Soviet captain decided that war had begun and ordered a nuclear torpedo to be launched. The officer agreed, but the second officer, Vasily Arkhipov, convinced them not to fire. The Third World War did not happen then, nor has it ever happened since, because if it had, none of us would be here. In a multiverse interpretation, we cannot exist in the branch where this happened because we would be dead. In this sense, all of history is a sequence of unlikely events that led to the emergence of us humans. And in different branches of reality, there are doubles living their own lives. There's a branch where you became president, where you cured cancer, where you never lost that person you loved. Even critics of quantum immortality agree. At any future moment, there is a branch containing your living successor. Maybe somewhere Hugh Everett is still alive. 94 years old, Nobel Prize on the shelf, great-grandchildren playing on the carpet. David Lewis is there too, smiling, ready to pick up their old debate over a game of chess. Among these branches, we can imagine all our hopes and dreams, our aspirations for a better world and a happier life. And although we will never be able to enter the branches of reality where we made different choices, where our loved ones live longer, where history took a different course, these realities exist. This proves that any dream is achievable, and this can be a source of inspiration and comfort.